Okay, in this video, I'll be going over the Chapter 14 exam study guide. So number 1 says, balance each equation and write the reaction quotient, QC. So what reaction quotient is it's just the concentration of each, like, what's it called, product, um, over the concentration of each reactant, sorry. So it looks something like this, basically. So it's the quotient of the two products on the numerator divided by the quotient of the two reactants on the denominator. And it's all concentrations, which is what the brackets mean right here. So for problem A, it's the reaction between ammonia gas and oxygen gas, which makes nitrogen monoxide gas and gaseous water or steam, basically. So first, let's try to balance this. So there's one nitrogen here, three hydrogens here, two here, two oxygens here, and two oxygens here. So the only thing wrong with this is the hydrogens. There's two and three. They're not equal. So in order to change that, we want to find a multiple between 3 and 2, which for this case it's 1.5. Okay, but we don't want like what's it called, fractions, basically the 0.5s. We don't want 0.5s there. So in order to get rid of that, we multiply everything else by 2, or everything by 2. So it's by 2, times 2, times 2, times 2. And what this does is it multiplies the coefficient of each reactant and product by 2. So that makes 2 ammonia gas, 2 oxygen gas, 2 nitrogen monoxide gas as well, and 3 water vapor. Oh, sorry, gas here. So let's go ahead and count it again. There's 2 nitrogens, 4 oxygens, 2, and 5 oxygens here. So now that's bad. There's 4 here, and 5 here. So in order to balance that out, we put 0.5 in front of this thing right here, from the oxygen gas. Now that makes another 0.5, another fraction, which we want to get rid of again by multiplying everything by 2 again. So now it's 4 ammonia gases, 5 oxygen gases, 4 nitrogen monoxide gases, and 6 water vapors. Now it's balanced. See, 4 nitrogen, 12 hydrogen, and 6, 10 oxygen, 10 oxygen right here. So this is balanced. This is good. Now for the QC, we want to convert like each coefficient in front of its respective molecule into an exponent. So I forgot to add that here too. It's C, D, A, B. So whatever is in front of these species becomes their exponent. So we'll do that here. So for nitrogen monoxide, it's got a 4 exponent, so it's the 4th power. Our water vapor has a 6 exponent. Our ammonia gas is to the 4th power. And the oxygen gas is to the 5th power. That would be it. That's what you want as your answer. So I'll go ahead and box that. Now for the second problem, it's the reaction between solid sodium and liquid water to make sodium hydroxide solution and hydrogen gas. So there's one sodium, that's good. Two hydrogens, three hydrogens here, that's not good. But one oxygen, that's good. So the only thing not balanced is the hydrogen. So in order to temporarily balance it, we want to put a 0.5 right here. Let me get rid of that. 0.5. Now it's a 0.5. Like I said for the previous poem, I'm going to get rid of that by multiplying everything else by 2. So that makes 2 sodium, solid sodium, 2 liquid waters, 2 sodium hydroxide solutions, or aqueous solutions, and 1 hydrogen gas. So there's 2 sodium, that's good. 4 hydrogen, 2, 4 hydrogen, that's good. And 2 oxygens, 2 oxygens, that's good. Now for the QC, what I forgot to mention earlier was that we only count the gaseous and aqueous um, species in this because, as you see here, it's QC. This is the reaction coefficient of concentrations. And you see, for solid stuff, there is no concentrations. It's just all all throughout. It's just that like one thing basically. For water doesn't have a concentration. It's what makes like the concentrations. You know what I mean? Like in a solution, it's like a concentration of blank in an aqueous solution. That basically means it's dissolved in water. So water can't really have a concentration. This aqueous means it's a solution, which means this does have a concentration. We don't know what it is, but we just know that it does have a concentration. And for gases, it's kind of the same as aqueous solutions, but this is dissolved in in the air, basically. So that means we're only going to count the hydrogen gas and the sodium hydroxide solutions. So instead of dividing it by these two, we're not going to divide it by anything at all. So we're going to get rid of this little bar right here. And just put the products. So it's NaOH squared, since that's the coefficient, multiplied by the concentration of hydrogen gas. That'll be it for this problem. So it's pretty straightforward. Just keep in mind that you only count aqueous and gaseous species, not solid or liquid. That should be the first problem. Okay, so number 2 asks, find Kp for the following equilibria. So let's start with A. So here on top we have the equation to find Kp. Okay, so the reason I chose this equation is because we're given the Kc right here, and the only equation that is related to Kp that also has Kc in it is this one right here. So that's kind of how you want to look at the problems you're given. You want to see like what you're given or what you could find and how that relates to I don't know what equation you're trying to use basically. So let's plug in the numbers. Or actually first let's find all our numbers. So Kc, it's pretty obvious, it's this one. R is kind of trickier because we have 2 R's, remember? R could either, or could be either 0.8, you know, 0.821 liters times atmospheres over moles degrees Kelvin, or 8.314 joules per moles times Kelvin. So we're solving for Kp, and P means pressure, so we're working with gases. And gases have atmospheres, or that's like the pressure of the gas. And the only R that has atmospheres in this is this one right here. The R equals 0.0821 liters times atmospheres over moles times Kelvin. So that's kind of how I would look at it. And T is kind of obvious. It's at 1000 degrees Celsius, or I mean Kelvin, point Kelvin. So we use that. Now for moles of gas, we want to think of the products as the final and the reactants as the initial. Or a change in anything um is final minus initial. So a change in moles of gas is equal to the number of moles products minus the number of moles of reactants. So on the products, only 1 mole of what's it called? I don't even know what this is called, but there's only 1 mole of this. And on the reactants, there's 2 moles. See, 1, 2. So we kind of think of it like that. So 1 minus 2 equals -1. So our exponent here is going to be -1. So let's go ahead and solve it. So Kp equals Kc, which is 3.9 times 10 to the -2 times R, or 0.0821 liters times atmospheres over moles times Kelvin times our temperature, which is 1000 degrees Kelvin, all to the -1. Or not all to the -1, but this is to the -1. And that should give us an answer of 4.8 times 10 to the -4. And since we're working with equilibrium constants, we don't need like units. So you don't have to do all this, but I just kind of like doing it because I kind of like keeping track of things. Or maybe you should do this because Schultz might be a little picky about showing units and stuff. So for number 3, it's basically the exact same like scenario as A. Or I mean palm B is the exact same scenario as palm A. So our Kc is given to us. It's 1.67. So I'll just label it as that kind of, even though it's already labeled. But our temperature is 500 degrees Celsius. Our change in number of moles of gases is -1 as well. So all that's left is just plugging in like everything in. So Kp is our Kc, so 1.67 times R, same R, liters times atmospheres, moles times Kelvin. I'm pretty sure the atmospheres here is switched the liters, but I don't really think it matters. That's just how I like. What's it called? I'm used to writing it for some reason. So that's times our R, or I mean our temperature, which is 500 degrees Kelvin, raised to the -1 power. That should give us a reaction constant for partial pressure at 0.0407, and that should be it for this problem. Okay, so number 3 says at a point during the reaction below, the concentration of N2O4 is equal to 0.12 molar, and the concentration of nitrogen dioxide is equal to 0.55 molar. Is this reaction at equilibrium? If not, in which direction will it progress? So when it asks to determine whether it's at equilibrium or not, you want to solve to see if QC is equal to Kc, because Qc is the reaction quotient of concentrations, and Kc is the equilibrium constant of concentrations. So I think of it as like, what's it called? As this. I put QC on the side of the reactants, and KC on the side of the products. So if both are equal, they're at equilibrium. But if one is larger than the other, then the reaction is in favor of that side. So let's say QC is larger than KC. That means the reaction is geared more towards the QC. Like in other words, the reaction uh, favors the reactant side. You know, but if KC is larger than QC, it's the opposite. The reaction favors the products. That's how I see it. So we want to solve for both QC and KC. We already have KC here, so we don't have to find that. But for QC, we want to set up the quotient. So they're both gaseous, which means we could use both of them. So is the concentration of nitrogen dioxide with a 2 power, since it's got a 2 coefficient right here, over the concentration of N2O4. So we're actually given the concentrations in the problems. So we plug those in to solve for QC. So the concentration for NO2 is, let me measure. It's 0.55 to the second power. You don't gotta put molar since it's a quotient. It won't have units at the end. Over 0.112 or 12. I mean, sorry. That should give us a QC of 2.5. Yeah. So our KC is 0.2, our QC is 2.5, which means our KC, or I mean, our QC is larger than our KC. Let me just write that out. So QC is larger than KC, 0.21, which means this reaction favors the products. Which means since they're not equal with one another, they're not at equilibrium. So not at equilibrium. And you also put like reactants favored, since it asks in which direction you'll progress. You just want to like state which side is favored, basically. So that'd be your answer. Along with all of this too, because you want to show your work for this stuff. That should be it for number 3. Okay, so number 4 says, for the reaction between ammonia and oxygen gas, a flask was filled with 2.40 molar ammonia gas and 2.40 molar oxygen gas at a particular temperature. At equilibrium, the concentration of dinitrogen tetroxide equals 0.134 molar. Calculate Kc. Okay, so this kind of has a lot to it. So you see, we're given the initial concentrations of ammonia and oxygen gas, and we're given the final concentration at equilibrium of N2O4, one of our products. So what that kind of tells you is we're gonna have to do an ice table. So let me just do that for you guys. So that's kind of what you would start out with. You see, we have the initial concentrations and everything that doesn't or wasn't given to you for the initial concentrations has a 0 right here. Okay, so now we want to go ahead and like define our variables. So you see, we kind of want to like, what's it called? Go with the coefficients right here. So I would put the lowest coefficient as x and scale everything to that. For 7, for the O2, you kind of want to divide it by 2 to get your x. So it'd be 3.5x. For 4 NH3 gas, you could divide that by 2 to get a whole number, so 2x. And here, it'd be 3x. So that's kind of how you want to do it if there's no like clear, like just like lone species here. Um, and in the problem, we're given the, what's it called? The equilibrium concentration of N2O4, which is 0.134 molar. So this was actually going to be our X, basically. So this is what we want to replace everything else with. All the other equilibrium concentrations, we want to like add or subtract X to this. So I forgot to put this, but remember for reactants, it's negative X. And for products, it's positive X. So for the gaseous water, or the water vapor, is 3X. You just want to multiply 3 by X, which, as we said, it's 0.13 molar. 134 molar, sorry. So that should give us a equilibrium concentration of 0.402 molar. So that's going to be our equilibrium concentration for water vapor. And to this, and to the reactants, I mean, since we're actually given an initial concentration, we actually want to subtract from the initial concentration what we have for the x's. So it'll be 2.40 molar minus 3.5x. And instead of x, like I said, it's 0.134 molar. So it's kind of a tight fit in here. But that should give us a concentration of 1.931. Okay, and that would be the same for both, or not both actually. I'm sorry, since this is a completely different number. So for gaseous ammonia, we do the same thing, minus 2x, so 2 times 0.134 molar. That should give you 2.132 molar. I just realized I forgot the 4 for this, but I calculated it with the 4 included, so it should still be the correct answer. So now to find the Kc. Remember, Kc is the concentration of the products raised to the respective exponent. So our first product is N2O4, and the coefficient is 2. We bring that down and square it. Our next product is water vapor. It's got a 6 coefficient, so we put a 6 exponent here. We divide that by the concentrations of our products, or I mean, our reactants. So for ammonia, it's that raised to the 4th power. And for oxygen gas, it's raised to the 7th power. So for this, we replace everything with the equilibrium concentrations we just solved for. So these things right here. So let's go ahead and do that for you guys real quick. So this is what it should look like in the end, and doing all that gives us an answer of 2.01 times 10 to the negative 7th power. That would be our Kc for this problem. So kind of what you gotta do for this problem is you kind of have to set like the lowest exponent, like holding species, to 1, and base everything else around that in order to get an easy calculation. Because if we would have like set this as 2x instead. We would have to like do a whole bunch of other stuff to solve for x, and it's really not worth it to have. So yeah, that should be it for this poem. Okay, so number 5 says, how does an increase in temperature affect the products of each reaction below? So first one, you gotta remember that heat can either be a product or a reactant of a reaction. So if the first one, for example, for the first poem, it's an endothermic reaction. I mean exothermic reaction because we're releasing heat. Okay, which means since we're releasing heat, we're making heat. Heat is a product, so we just add that as one of the products to help visualize. And an increase in temperature means we're like adding more heat basically. So we're adding more product because of that. Um, and for reactions, kind of think of them as having like a mind of their own. Like if one side is unbalanced, then it starts like favoring the other side. You know, like if there's more products on one side than there are reactants, then the reaction is going to shift to favor the reactants to make more, to bring it to equilibrium. So if the temperature is increasing and heat is one of the products, we're getting more products because of that. We're getting an increase in products, and the reaction isn't at equilibrium anymore, which means the reaction itself starts shifting towards the reactant side to start favoring those, start making more of those to bring the reaction up to equilibrium, which means it's taken away from the products. So the answer for A would be a decrease in products. You can put an arrow. You should write it out actually. Write it out as like decrease in product, and outer box that just in case. So this is the only problem, or this is the only answer you kind of need to give: just an increase or decrease in products. And for B, it's the opposite, where now it's an endothermic reaction. We have heat as a product. Okay. So since the temperature is increasing, we're getting more heat. Okay, which means it's kind of the opposite of problem A. We have more reactants and less products, which means the reaction is going to start favoring the products and making more of that, which results in the amount of products increasing and the amount of reactants decreasing. But we're only worried about the products, so we just could put increase in products. And that's kind of how I would like to visualize it. You see, we're getting more from one side, which means the reaction is shifting towards um, the other side in order to reach equilibrium once again. It's making more of the other side to compensate for the increase. Another way you could like say it is like, remember in lecture, an increase in temperature means a decrease in in Kc for exothermic reactions, which is kind of the same thing because remember Kc, the lower it goes or the closer to zero it is, the more the reactants are favored. Okay, it's kind of it kind of mirrors what I put here. Since we're increasing the temperature, our Kc is dropping, which means we're making more products. Okay, having less, or I mean, we're making more reactant and having less products. And for X or for endothermic reactions, is the opposite kind of. It's what's it called? They're they're proportionate to one another. So an increase in temperature is an increase in Kc. And that makes sense because the higher the temperature, the more products we're going to have, which means the more, the more reactants we're going to have, which means the more favored the products will be, which is why the Kc is increasing. The higher the Kc, the more like favored the products are, basically. So you can look at it in either of those two ways. I like to think of it as kind of like this box because it's easier to visualize. But whatever floats your boat, to be honest. Well, that'll be it for number 5. Okay, so problem number 6 says the molecule D2, deuterium, undergoes a reaction with ordinary H2 gas. For the reaction below, Kc is equal to 1.80 at 298 degrees Kelvin. If the enthalpy of reaction is 0.32 kilojoules per mole of DH, calculate Kp and Kc at 500 degrees Kelvin. Will the highest yielded product be achieved with a high or low pressure? What about a high or low temperature? Okay, so let's start off by solving for the other Kc. To do that, we need to use this equation right here. It probably has a name for it, but you don't gotta know the name for it. You just gotta know that it involves two K's. It could be either Kc or Kp's. It doesn't really matter which one. It depends on the context. So for this poem, it's Kc's. So we're gonna put it as Kc's. So our Kc1, like the problem said, is 1.0 or 1.80 at a temperature of 298 degrees Kelvin. Our R is 8.314 joules per mole times Kelvin. And this differs from the previous poem where we used R because unlike the other one, which is 0.0821 liters times atmospheres per moles times Kelvin, we don't have volume or atmospheres. We only have joules. See, joules right here, which means we don't use this one. So first off, let's convert the heat, the enthalpy of reaction into joules because right now it's in kilojoules. We want it in joules, so we just multiply by 1,000 and we get 320 joules per mole. So that'll be our enthalpy of reaction. Our R is already this, like I said. Our T1, this. Our T2 is 500 degrees Kelvin, and we're solving for Kc2, which means we want to rearrange this entire equation to just solve for that. So the first thing we do is we get rid of the natural log. So in order to get rid of that, we raise both sides to the power, or we raise both sides to e. So that's how it will look like. It'll be Kc2 over Kc1 equals e to the power of this entire thing right here. So it'll be enthalpy of reaction over R times 1 over T1 minus 1 over T2. Now to just isolate Kc2, we multiply both sides by Kc1. So Kc2 equals Kc1 times E raised to all that. So all that's left now is to plug everything in to solve for Kc2. So everything plugged into here looks like this. It's kind of wonky from my handwriting, but you get the picture, right? So solving for that, we get 1.89 or not 89, it's 1.90 since it rounds up. So this is our KC2. What I did was I put this entire thing also in parentheses to prevent any mix-ups, like during calculations. And how Professor Schultz does it is he keeps everything like in one neat line by raising everything like by raising fractions to the -1 power instead of writing them out like this. So I'll show you guys what that looks like. So e to the 3 point or 320 joules per mole times 8.314 joules per mole times Kelvin, to the -1 since it's in the bottom of a fraction, times 298 degrees Kelvin -1 times 500 degrees Kelvin up to -1. That's how he does it. That might look better if you were using like a scientific calculator, but since I use a graphing one, it looks like it looks better for me to use it like this. That's not I'm used to it, but to each their own, I guess. It should give you the same answer regardless. Now to solve for Kp, we use the equation we used in problem number 2 to solve for it. So it's Kp equals Kc times R T times change in moles of gas. So we have Kp, we have a temperature. Since we solved for Kc2, we're going to be using this to solve for that because the problem asked to solve for Kp and Kc at 500 degrees Celsius. So we're just keeping the numbers uniform or consistent, I mean. So this is our Kc, our R. Since we're dealing with moles of gas, think of gas as in like atmospheres. And the only R that has atmospheres is the one we didn't use earlier, the 0.0821 liters times atmospheres over moles times Kelvin. So we're gonna use that. And our temperature, like I said, is 500 degrees Celsius, 0 degrees Celsius. So plugging everything in, it should look like this. Kp is Kc, so 1.90 times R, 0.0821 liters times atmospheres, moles times Kelvin times temperature, so 500 degrees Kelvin. To change the number of moles of gas, number of moles of gas, we look at the equation below to solve for the change. You see, there's 2 moles of gas here, there's 2 here, which means in reality, our exponent is going to be 0. So we just get rid of this entire thing since anything raised to the 0 power is just 1. So in reality, our Kp is 1.90. That's our Kp right there. In order to answer the second part of the question, we kind of have to visualize it. So think of like 2 containers. Okay. So one has a lower pressure. Think of this as like a piston. One has lower pressure. There's a lot of gas in there. And they're floating around pretty much freely. You see, there's not much not many interactions going on. But if you have a high pressure like this, you're squeezing all of the reactants together, like making them faster and causing them to form products faster or at a higher rate compared to this side right here. Which means with a higher pressure, you're getting more products. That's kind of how you want to visualize it. Now for the temperature, remember this reaction is endothermic, which means the reaction has heat as one of the reactants. So if we increase temperature, we increase the number of reactants, causing an imbalance, which means the reaction will shift to make more products in order to reach equilibrium. So you want to choose a higher temperature because of that. Kind of think back to the previous problem for number 5. It's kind of the same principle. An increase in temperature means an increase in Kc, and the higher the Kc, the more like the reaction is favoring the products. And the lower the temperature, the lower the reaction is favoring or the less the reaction is favoring the products, and the more it's favoring the reactant instead. So to answer the question, it'd be a high temperature and a low pressure. That will make the yield the highest. Number 7 asks, the reaction below has a Kc value of 120 at a particular temperature. Its container holds the following concentrations. Concentration of N2 is 0.100 molar. Concentration of O2 is 0.100 molar. And the concentration of NO is 0.200 molar. When the reaction reaches equilibrium, what is the concentration of NO? So it should be, well, it shouldn't be obvious, but I feel like you guys should like start getting used to like knowing what the signals are for making ice tables. If you're given initial concentrations, and if you're given, or if you're asked to find concentrations of a specific product or reactant at equilibrium, that basically means you have to make an ice table. Okay, so let's go ahead and do that. So the initial concentration of O2 is 0.100 molar. Same for O2. And for nitrogen monoxide, it's 0.200 molar. So let's go ahead and not divide, but define the variables. So here, since it's a reactant, it's negative x. Same here. And for NO, or nitrogen monoxide, since it has a coefficient of 2, compared to N2 or O2, it's double that. So instead of just 1x, we put 2x plus 2x. Now our equilibrium concentration should be equal to the initial minus the variable. Initial minus the variable. Since we haven't found it yet, we're going to solve for x right now. So in order to solve for x, we want to solve for Kc first. Or not solve for Kc, but state what Kc is. So NO squared, since it has coefficient of 2. Oh, sorry, no, that's not right. Instead of using these species, we're gonna use the equilibrium concentrations, or what they should equal. So on top, it's going to be 0.200 molar plus 2x. And here it'll be 0.100 molar minus x squared, since there's 2 of them. And I forgot to put the square here too, since we still bring over the exponents for whatever has a coefficient greater than 1. So you see it's got a 2 here, you put a what's it called, a square here. Okay, so now the first thing we do is we get rid of the square. So to do that, we cube root both sides. So it'll be the cube root of Kc equals 0.200 molar plus 2x divided by 0.100 molar minus x. Okay, so now we're going to do some algebra to solve for just x. We want to isolate x by itself. So to that, we multiply both sides by 0.100 molar minus x. So I'm just going to go ahead and do that. 0.100 minus x. I get rid of this, and just imagine I do the same thing. Actually, no, I'll write it out. 0. And it'll look like this. So Kc times 0.100 molar minus x equals 0.200 molar plus 2x. Now next step is to distribute the Kc, or the square root of Kc, into 0.100 molar and into negative x. So that'll give me Kc times 0.100 molar minus square root of Kc times x equals 0.200 molar plus 2x. Now we're going to remove the minus Kc, or the minus square root of Kc times x to the other side. So to that, we add it to both sides. So I'm just gonna put this side on the other side real quick, because that's how I kind of like to view it. I like to view the x as being on the left side of the equation, but nothing will change if you don't do it like this. Just makes it easier to understand for me. It's kind of like that. Okay, now we want to isolate the x's further by just having the x variables here. Or I mean like the x like terms here. So I'm just gonna keep these here. So we subtract both sides by 0.200 molar. 200 molar. So now it's running out of room here. 2x plus square root Kc times x equals square root Kc times 0.100 molar minus 0.200 molar. Okay, so now we want to factor out an x from both terms. So it'll look like this. So x 2 plus square root of Kc. And I'm going to do 2 steps in one right here. And not show the work on this side, but it'll be x equals square root Kc times 0.100 molar minus 0.200 molar, all divided by 2 plus square root of Kc. So what I did in this missing step, I just divided both sides by 2 plus Kc, or the square root of Kc. So this is what we're going to use to solve for x. It's kind of like a long process, but I just write kind of big to show you guys like in detail. So after cleaning up a little bit, this is what you should have. So just plugging everything in, it should look like this. X equals Maybe frustrated. Yeah. So the square root of Kc, which we're given, it's 120 times 0.100 molar minus 0.200 molar divided by 2 plus the square root of Kc, which is 120. So that should give us an answer of 0.0691 molar. So that's going to be our x. We're going to replace everything here, or every x here, by that in order to solve for equilibrium concentrations. So it would be 0.100 molar minus 0.02, oh sorry, 691 molar and 0.200 molar plus 2 times 0.0691 molar. So our equilibrium concentration should be 0.0309 molar. Same here, 0.0309 molar. And here for the nitrogen monoxide, it should be 0.3302 molar. That's what the problem is asking us to find, the equilibrium concentration of NO. So that would be the answer you box. You could box these as well, but Professor Schultz is just looking for the this specific one right here. And that'll be it for this problem. You could go back to like before I erased this to see how I solved for this. But it's pretty much just algebra. You know, you want to isolate the x, so just play around with it and see how you can isolate the x, and you should get it. Okay, so number 8 says the decomposition of ozone is shown through the following multi-step equation. Balance each step, write the overall balanced chemical equation, and prove that the overall equation reaction quotient is equal to each step's reaction quotient. So looking at this first equation, it's already balanced. See, there's 3 oxygens here, 1, 2, 3 right here, and same here for the second reaction. So we don't gotta worry about that. Which means we just go ahead and find the overall equation. So remember, for these multi-step equations, whichever species that are the same but on opposite sides of the equation right here, must cancel out. Okay, so it doesn't matter if they're in different steps. Like if it's oxygen, for example, this cancels out, and so does this, because they're the same species but on different sides of the equation. Okay. I don't know why I did that. So let's go ahead and cancel those two out. And whatever is left gets added on to what's below. So our overall is 2O3, or ozone, makes 2 oxygen gas. I mean 3, sorry. 3 oxygen gas. Okay, so there's 6 oxygen, 6 oxygen, that's good. Now for the overall QC. Remember, it's concentration of products and their coefficient as exponents over the concentration of reactants and their coefficient as exponents. So we want each step's QC right here to be equal to the overall's QC. Okay, so let's start off by finding each step's QC. So um, disregarding all of this stuff right here we just did, let's try to find the QC. Let me just clean it up real quick. Okay, so like I just did, it's the products over the reactants. Same here. Products over reactants. So let's bring those down. Let me rewrite them again real quick so I can show you guys what it is. Or first, let's do the equation. QC is equal to Q1 times Q2 times Q3. Oh, overall, sorry. Overall. Overall. So that kind of means like this QC right here, this overall equation QC is equal to the product of each other step's QC. So let's go ahead and do that. Okay, so how you prove these are equal to one another is we want to cancel everything that's like on opposite sides of the fraction. So oxygen, for example, there's one oxygen here in the numerator. Oh, there's one oxygen here in the denominator. So we cancel them out. Oh, and what's left is we multiply this O2 by this O2 to the second power. That makes O2 cubed. Oh, and we multiply this ozone by this other ozone. So that makes ozone cubed, or I mean squared. Sorry, squared. Oh, and you see that's equal to the quotient of the overall equation, which is the exact same thing, like I said. So that's how you prove it, or that's how you prove the overall QC is equal to each step's respective QC. That should be it for 8. Okay, for number 9, this one's kind of trickier. It asks, in a sealed 15.0 liter container heated to 298 degrees Kelvin, 0.150 moles of calcium carbonate and 0.150 moles of calcium oxide are placed, bringing the partial pressure of carbon dioxide to 0.250 atmospheres after equilibrium is reached. If an additional 0.275 atmospheres of CO2 gas is added, what is the total mass of calcium carbonate after equilibrium is once again established? Okay, that was a lot. So let's work through it like step by step. So we know equilibrium is established 2 times. So what we can infer from that is we gotta make 2 ice tables. One for the first time equilibrium is established, and one for the second time. So we're gonna go ahead and do that first. So now you might think, oh sorry, this is sweet solid. You might think, oh, that's since calcium carbonate and calcium oxide are solid, we won't use them at all, right? But wrong. We are going to use them. Because if we write out Kc, it'd just be the concentration of CO2. But as you see here, we have no initial concentration of CO2 gas. We just have initial concentrations of both our solid products and reactants. So we're gonna have to like like work around that basically. So start off with the initial concentrations. Well, not concentrations. Oh, since it's just moles, but we can't really divide moles by liters here, since it's solid. Not like what's it called? Not it's not being dissolved because it's not a gas right now. Nor is it in the liquid. It's just in a container. So we can't divide it by the 15 mil or the 15 liters. So let's go ahead, define the variables, negative x minus x, or sorry, plus x. Since this is a product, plus x, plus x. Okay, so what do we solve for here? Well, right now we're working with just moles right here. So what I can infer from that is we should also get some amount of moles here. Oh, but how we solve for this if we can't use the Kc equation, right? Well, we have to use something else. You see, we're given the pressure. Our volume is 15.0 liters. We have a temperature of 28 degrees Kelvin. And we assume, since it's a constant, we have an R. 0.0821 liters times atmospheres times moles per liter, you already know. Or times moles, or over moles times Kelvin. That's what I meant. Oh, so seeing this, you kind of like should assume that we use PV equals nRT to solve for x. So n is going to be what we solve for in number of moles, right? Just rearrange to solve for n. It's n of CO2. Let's just define it as that. So n of CO2 equals PV divided by RT. So let's just solve for that then. So on PV, so the pressure 0.220 atmospheres times volume, so 15.0 liters, divided by R times temperature, so 0.0821 liters times atmospheres, moles times Kelvin, times our temperature, so 298 degrees Kelvin. So solve for that, we should get 0.134 moles, sorry, moles of CO2. So that's going to be our x. 0.134 moles. So what's our x found? We're going to plug it into both of these equations right here. So 0.150 moles plus 0.134 should be 0.284 moles. And subtracting it from this, it should be 0.16, or sorry, no, 0.16 moles. I'm not gonna write it out like how I did here because I'm a little lazy. But that's gonna be what we use for this second ice table. Okay, so this is what we're gonna use for our second ice table. So, let me just draw it real quick. So this is what the second ice table would look like. The only thing different here though is that the variables are switched. Or the signs at least are switched. Why? Well, because you see from the context of the problem, we add product in there, which means we, like how I said like earlier in this video, you kind of want to think of it as like having a mind of its own. So you added more product in there, more CO2, the 0.275 atmospheres of the CO2 was added. That causes an imbalance here because there's less now. There's less. There's less reactants than products now, which means the reactions starts favoring the reactants now. So the rules are reversed now. Instead of having positive exponents here, now they're negative because the positive side is the side being favored. So that's how I would like look at it. You kind of want to be like aware of that because if not, it's gonna mess up your whole like process. Now to find this, so to find the initial concentration of our CO2, we actually want to use the 0.275 atmospheres given to us for the second part of this problem and convert it or use it to find a number of moles again. And with that number of moles, we're gonna add it onto our equilibrium concentration just to like to find the initial one for this ice table. So I'll just go ahead and do that real quick. So this is what it should look like after you go ahead and find the number of moles of CO2. So this is what we solved for, and we just added on top of that the x value here. Since what's it called? Since equilibrium was established in this first portion right here, the number of moles doesn't change. We're just adding on to it with the 0.275 atmospheres of CO2. So they just add together to create a big old sum, which is 0.303 moles. And now we're just gonna go ahead and subtract and add our x value, which is just 0.134. It is kind of a coincidence because if we subtract what we just added in here, it would just end up the same number again. But you gotta show your work for this part. Or for this stuff, I mean, sorry. Oh, hold on. Forgot to add the number of moles here. So that'll be 0.169 moles. Okay, it's our equilibrium concentration, quote unquote. So here we do the same, subtract 0.134 moles, and here we add it plus 0.134 moles, just squeeze it in there. So with that, it actually turns out to be the exact same answer for both of these. So 0.15 moles, 0.15 moles. Now, to find the mass, we just convert the number of moles of calcium carbonate into a number of grams using the molar mass. So 0.15 moles CaCO3 divided by 1 mole. And the molar mass is 100.086 grams. That should give us a mass of 15.0129 grams calcium carbonate. But this number has 2 sig figs, so we just round the 2 sig figs, so it's just 15 grams. Yeah, that'll be your answer. So in my opinion, this is one of the harder problems, or the hardest problem from the study guide because you've never really done 2 ice tables. I don't think you guys have done 2 ice tables in lecture before, so this was briefly covered as one of the slides for lecture, which I think doesn't really do it much justice. So if I were you, I'd practice this like the most because it is kind of confusing. Okay, number 10 says, oh, be able to know the differences in size between Kc and Kp when it comes to gaseous equilibrium. When a reaction has less moles of gaseous products than gaseous reactants, how will Kc and Kp differ in size? So when you think of number of moles, you should think of the equation of Kp equals Kc times R T raised to the power of the change in moles of gas. Or N of gas, since N is the same as moles. So if you have a larger number of moles right here, or like, let me write it out in a generic formula. C plus D. So if you have more moles on this side, remember the change in number of moles of gas is final minus initial. Final minus initial. This side has 3 moles of gas minus 2. Actually, that's a bad example. Let me make it like a 4 right here. So if the product side has a larger like difference in moles than the reactants, you have a larger exponent here, which means your Kp will be larger because of that. If you had like an equal or like what's it called, less gaseous products, then your exponent would be -1, because n gas is equal to 1 minus 2, final minus initial, which means this right here would make a way smaller Kp than if you had like a power 3 instead. So you kind of want to think of it like that. So if the change in number of moles of gas is greater than 0, basically, then Kp will almost always be greater than Kc, unless Kc is already large to begin with. But if the change in number of moles of gas is less than 0, then it would be Kc that's larger than Kp. If it's equal, however, equal to 0, then they'll be equal to one another. In other words, they'll be in equilibrium, basically. That's kind of how you should see it. The larger the positive change in moles of gas is, then the greater Kp is going to be like compared to Kc, and vice versa. You should explain this in your own words, or be able to explain this in your own words. So in other words, I would say it's dependent on whether the products has more or less like moles than the reactants. That should be it for this poem. This should be one of the easier ones. It's just like explaining in full sentences or short sentences. And let me see. Anything else? I wouldn't worry too much about what's it called? The simplifying assumption or the quadratic equation for now, since you guys will most likely not see it in the exam, which I'd be happy about if I were you, to be honest, because I hate using that stuff. I think that's it for this video. Any feedback is welcome, and see you guys in class.